Welcome to the podcast of conjugate acid-base pairs. This is going to have a lot of applications for both buffers, determining buffers, because obviously a buffer has to be a conjugate acid-base pair, and also for determining the whether salts are acidic, basic, or neutral. Because you'll have to identify conjugate acid-base pairs in those and write their dissociations. So let's start with a weak acid. So we'll start with HF. That is a weak acid. And let's write the dissociation for that. So we know that this breaks up. You can also write this with water. The only difference is you'll get the hydronium ion instead of H+, and they're really the same thing. All right, so we're going to circle the H+, because that's what's going to determine our pH. That's what makes it acidic. And we'll label this. This is our weak acid. I'm going to use abbreviations here. And this is our conjugate base. Now, technically, a conjugate base just is a weak base. So you have a weak acid and you have a weak base, and they're conjugates of each other. They come from basically, they're interchangeable with each other. So if I add acid to one, it'll form the HF. If I add base to that, it'll form the conjugate base. So they go together. All right, why would we call this a conjugate base? Well, if we take F-, and we'll talk about how we could actually get F- in a second, but let's say we have F-, and we add this to water. Now, because this is a base, we always have to add water. We always have to add water to weak bases. And what do weak bases do? Well, they're going to steal a proton. So where are they going to get that proton? This is why we have to add water. They're going to get it from the water. Okay? So now that is going to form your weak acid again. So technically you could call this a conjugate acid. I just like to use the term conjugate for the one that you're not going to find on a table. So for example, when you go to look up Ka values, Kb values, you're going to find the Ka for HF, but you're not really going to find anything for F-. So it just helps to remind me. Plus, I always kind of think of the conjugate bases having to come from salts. So that just helps me to remember that. But there's no technical rule for that. All right, so back to our equation here. We also have to remember that what is left over from the water would be OH-. That's what makes this basic, because it generates an OH-. Okay? So now, how would we actually get F- into water? Because there's no F- on the shelf. You're going to have to add in a salt that contains F-. And obviously the two most common are going to be NaF or KF. And the reason why these are always, sodium and potassium are going to be your great cations to choose, are going to be because they're water soluble and they do not change the pH. So they're considered pH neutral. So if you add NaF to water, you're going to get Na plus F-. If you add K plus, you're going to get K plus F-. Both of these are spectator ions that we're not really going to care about. So in both cases, you're going to end up with F-, and then you can do the reaction. We'll go through the reaction right here, the dissociation, to generate a base. So the K really isn't going to interact with this equation here. That's going to take place once that F- dissolves. All right, let's take a look at a basic example. So let's start with a weak base. We'll use a simple one here. We'll go with NH3. That's ammonia. And because this is a weak base, we have to add water to it because it needs something to steal. And remember, in every acid-base problem, you're adding water. Just in some of them, you have to show it in the equation, and in some you don't. That's going to generate ammonium. Oops. Jump slides there. So this is going to be our weak base. This is going to be our conjugate acid. Why do we call this a conjugate acid? Well, if we were to add that to water, and since this is an acid, I don't have to write the water. You can. It's correct either way. We end up with NH3 and H+. We know that anything that generates H+ gives up an H+ is a acid. So this is our conjugate acid. Whoops. And this is our weak base. Well, how would we get NH4+ into water? We would need some anion to go with it. So the best choice is actually going to be, forgot the 4, is going to be NO3 because that is also pH neutral and it won't form any precipitates. But a lot of times you'll also see something like NH4Cl. Cl is also a good choice because it's most of the time soluble and it's also a pH spectator. You could also choose NH4Br. You could have NH4I. All of these anions, I minus, Br minus, Cl minus, NO3 minus, they're all pH spectators. Another example would be NH4ClO4. Okay, so that when they dissolve, the bromine ion or the chloride ion or the nitrate ion, you're going to cross that out as a spectator, and it won't influence the pH. All right, so here's some practice problems, and if you want to try these quickly first, I'm going to go over the answers for them. So we're going to identify what the conjugate acid or base would be. So first of all, let's label all of these as weak acid, weak base. Okay, so this would be a weak acid. And with all conjugate acid-base pairs, you're really focusing on weak acids and bases because strong acids and bases are not at equilibrium. They're going to go to completion. So do they technically have a conjugate acid or a conjugate base to them? Sure, but they're not really going to be very effective. So first one's a weak acid, okay, because it starts with an H. The next one is also a weak acid because it ends in Cu. NH2, that would be a weak base. H, starting us out, would make it a weak acid. And again, we've got the nitrogen. Even if it doesn't have the hydrogens attached, that still makes it a weak base. A nitrogen hanging off the end there. All right. So now we're going to identify the conjugate that would go with it. So if we have the first one up here, this one is going to be, so I'm going to do number 1. If this is a weak acid, okay, then it's going to have a conjugate base. So a conjugate base is going to just have lost the hydrogen. All conjugate bases are going to have a negative charge. So it's going to be ClO3 minus. You have to think about, well, why is that? That's because it's lost an H+. So what's left over has to be an anion. Let's come down here to the next one. It's going to lose this hydrogen, right? Because that's the Cu, that's the acidic hydrogen. So you're going to end up with CH3. Don't break anything else up. Leave everything else together. Just drop the hydrogen and put a negative charge. Okay? So it's the same thing as this here and here. The only difference is this one has dropped that hydrogen and has picked up a negative charge. Well, what do weak bases do? So let's come down here to this next one. Weak bases don't lose something, they gain something, and they gain an H+. So the conjugate acid of this is going to be CH3, CH2, and again, I'm leaving that organic, all this stuff, I'm just leaving it alone. So this has picked up a hydrogen, and it's going to have a positive charge because it's picked up actually not a hydrogen, it's picked up a proton. So it's picked up an H+, okay? And all conjugate acids are going to have a positive charge because all of them are going to have an extra H+. Let's look at the next one. It's a weak acid. We'll have a conjugate base. We remember conjugate bases are negative. All we need to do is drop the hydrogen. That's going to be your conjugate base. And if we look down here, we've got a weak base, so we'll have a conjugate acid. Leaving all of this alone. So now it's got to pick up a H+, okay? So now we'll go back through and we'll just label these quickly. So this would be a conjugate base because it goes with a weak acid. This is a conjugate base. Again, it's going with a weak acid, and we notice that these have negative charges. This is a conjugate acid. It's got a positive charge, conjugate base, and a conjugate acid. Okay, now let's try a few. This kind of applies to salts, but we'll just practice a few. When you have a conjugate base, how they dissolve, and then how they're going to dissociate. So let's take the example NaOCl. Okay, so We know that this is going to be a salt, so we're going to break it up into Na plus, Cl minus. Oh, we forgot the O. Cl minus, okay? And we know that Na is a pH spectator. So the first step in this is this dissolving. Okay, this is a pH spectator. So this is not a pH spectator, and because it has a negative charge. So let's really highlight that there. It has a negative charge, okay? That means that it has to be a conjugate base, okay? And what do all bases do? Whether they're conjugates, any type of weak base, they're going to accept an H plus. In this case, if we're just dissolving it in water, it's going to accept that H plus from water. HOCl plus OH minus. That leaves us with an OH minus. So this is going to be your that's a C conjugate base. This is going to be the weak acid that it came from. And this here is your OH, which is what makes it basic. Let's try one more example. And if you need more practice with the salts, there will be a separate podcast just with salts and with categorizing. So let's take CH3NH3Cl. Okay, so this is obviously a salt because we see Cl here, right? And we know when we break up the salts, that will give us the natural split, okay, for the cation and the anion. So we're going to have, this is going to dissolve into CH3NH3 plus, right? Because it's going to be your cation, has to have a positive charge, and Cl minus. Okay? So the Cl minus is a pH spectator, and that means you're going to take your, and this has a positive charge, so let's highlight that. We'll draw it so we can really see it as a positive charge. So that means it's going to be a conjugate acid. So if it's a conjugate acid, what do all weak acids, all acids do? They give up a proton. So it's going to donate a proton. And so it's going to give up a proton, which is what makes it acidic. This is your conjugate acid. In the process, it'll reform its matching weak base. Okay, so let me give you a few to try. All right, so if you want to do the practice and try it for yourself, you may want to stop now because I'm going to go over the answers. All right, so we obviously have two salts here. One of the ways, again, we can know that there's that salt is we see familiar ions that we're used to, NO3, Na. We know that these are generally salts. Okay, so these are added to water. They're going to dissolve and they're going to break into their cation and their anion. So let's split these up. CH3 2 and H2 plus, okay, because it's a cation and has to have a charge. Remember, with these nitrogens, you can have a different number of hydrogens. Depends on how many of these substituent groups, that's these carbon groups, it has bonded to it. I wouldn't stress about that. Just know that the amount of nitrogens you have, when you split it up, it's still going to have a charge. All right, so NO3 minus. We know that this is a pH spectator. We'll get rid of it. And this, okay, because it's a cation, is going to be a conjugate acid. And we know that conjugate acids, when they're added to water, I'm just going to write it over here, they will give up an H plus, and you will be left with, oops, 2, okay, your weak base, and this will generate an acid water, a proton in water. So your pH will be below 7 when you dissolve this salt. Okay, so again, we would classify this because it contains a conjugate acid. We would classify this as an acidic salt. All right, so now let's take a look at the next one, and I'll change colors so we can see. With this one, it's going to split up into Na plus and C2. Of course, I chose the longest molecules or ions to write. Okay, Na is a pH spectator. Whoa, wait. Hold on a second. This is a 2 down here and a negative up here. Sorry about that. All right, so this is going to be your pH spectator, sodium, and you're left with the acetate ion. It's a negative charge. It's an anion, which means that you have a conjugate base. And we know what do conjugate bases do? They are going to accept an H plus from water. So we've got C2H3O2 minus. All conjugate bases have a negative charge. That charge is very, very, very important. And when we put this into water, because this is a base, we have to add water. It's going to be HC2H3O. Oops. 2 minus. And we're also going to generate an OH minus because it is a base. So, whoa, where's that? That negative charge does not belong there, sorry. It's hard to write at the edge here. 2. There we go. Plus OH minus. Okay. So this is going to be your weak acid. Okay. So let's just go through very quickly and highlight the acid-base pairs here. Okay. So this is going to be your conjugate acid that came from the salt, okay? And this is going to be the weak base that it matches. This is going to be the conjugate base that came from the salt. This is going to be the weak acid that it matches. So we have here a conjugate acid base pair, and we have here a conjugate base weak acid pair, okay? Thank you.